Okay, so as you may recall, this was the problem that we need to solve, balancing this redox equation. And basically, we have to go through the same steps as we did before. So let me do that in this case. So if you recall, the very first step in this process is that we separate this equation into two half equations. So one of the half equations would be this one. And the other half equation would be, I'm sorry, NO2 minus to form N2. All right. And then the next step is that we balance all atoms excepting oxygen and hydrogen in the traditional way, which means that in this case, we have to balance the sulfur here by putting a 2 here. And in this case, we balance the nitrogens by putting a 2 here. Then the next step says that we have to balance the oxygens by adding water to the side that needs it. Now, in the case of the first equation, we don't need to add any water because we already have the oxygens balanced. We have 6 oxygens, 2 times 3, 6 oxygens on the left side, and that balances with the 6 oxygens on the right side. In the case of the second equation, however, we have 2 oxygens here. We have none on this side, so we add 2 water molecules to this side, all right? The next step is that we balance the hydrogens by adding H plus ions. Again, in the case of the first half equation, we don't need to balance any hydrogens because there are no hydrogens present. However, in the case of the second half equation, we have 4 hydrogens here on the left, which means that we have to add 4 hydrogen ions here total on the right. And then the next step is that we balance the charges by adding electrons to the side that is higher in terms of the net charge. So in the case of the first half equation, we have a total of 2 times minus 2, so that's minus 4 on the left side. And here we have minus 2 on the right side. So what that means is that we need to add 2 electrons on the right side so as to make sure that we have a total of minus 4 on the right side, which balances with a minus 4 on the left side. Now, in the case of the second half equation, we have a total of plus 4 minus 2, which gives you plus 2 on the left side. And here we have 0 on the right side. So what that means is that we need to add 2 electrons to this side to make sure that the equation is balanced with respect to the charges. Okay, so let me, oops. Let me erase these here to avoid confusion. Okay, so the next step is that we have to make sure that the number of electrons are equal in both half equations. And it turns out that they're already equal. We have 2 electrons here on this side here. We have 2 electrons here for the bottom equation. So we don't need to multiply either equation by any number to achieve that equality in terms of the number of electrons. So therefore, we can cancel these out. And I don't think there's anything left to cancel out. So all we have to do now is rewrite what is left. So that would be 2s2O3 2 minus plus 4H plus 2NO2 minus. And then on the right side, we have S4O6 2 minus plus N2 plus 2H2O. And then we do one final check through to make sure everything is balanced. Use this pencil here. So we count the sulfur first. We have 4 sulfurs here. I'm sorry about that. We have 4 sulfurs here on the left, and we have 4 sulfurs here on the right. So that's balanced. As far as the oxygens are concerned, we have 6, 2 times 3, 6, plus 4, so that's 10 oxygens. And here we have 6 oxygens. Okay, wait a minute. Did I do something wrong? Something is not, the oxygens are not balanced. What did I do wrong? Oh, actually, the wrong thing I did was that I did not include these oxygens. So that's 6 plus 2, 8 oxygens, right? And here we have 6 plus 2, 8 oxygens. So the oxygens are balanced, actually. And then we have 4 hydrogens here. We have 4 hydrogens here. and then we have two nitrogens, and then we look at the charges. We have -4 from the two thiosulfate ions, +4 from the hydrogen plus ions, -2. So that gives you a total of -2. And over here we have a total of -2. So therefore, the charges are balanced as well. So this is basically how we do this particular problem. Okay, any questions about this example? Any questions?
Yes, the 2NO2, that would make that 4 oxygens? It would?
Yeah.
So then when you have...
Oh, I see what you're saying. Okay, let me see here. So you're saying the oxygens should be 6 plus 4.
That's what I'm asking, is did we have a mistake?
Yeah, okay. Thank you for pointing that out. Let me see here. Let me go back to the 2, 3, 6, 6. Mm. 2, 3, 6 plus 4. So that should be 10 oxygens on this side. We have 6 plus, okay, so what's wrong here? Let me go back to here. Okay, I think I see where I went wrong. I keep screwing up, okay. The mistake I made here is that this should be 4 water molecules. So let me erase. Thank you for pointing that out, by the way. Let me erase this here. So the equation is actually, the answer is actually more complicated. Okay, so here is a mistake I made. Let me go back to this. There should be 2 nitrogens there, but here you should have 4 water molecules, which means that here you should have 8 hydrogen ions, which means that the total number of electrons that you're going to need here is, let's see, 8 minus 2, so that's plus 6 on this side, 0. So this should be 6 electrons. So that means that this answer is wrong. Okay, so as you can see, it's very easy to make errors when it comes to these things. If you make an error somewhere, it screws up everything afterwards. Okay, so thank you for pointing that out, whoever said so, whoever pointed it out. So let me go back to this. So now what we need to do is multiply this equation here. Let me erase, avoid confusion. Let me erase this line here. Okay, so we have to multiply this equation here by 3 to make sure that the number of electrons lost and gained are the same. You have 6 electrons here, you have 2 here, so therefore this should become 6s2O3 2 minus to give 3s4O6 2 minus plus 6 electrons. And then we cancel out the 6 electrons here and here, and then we add what's left, and that should give us the correct answer. So that should be 8H plus 2 NO2 minus plus 6 S2O3 2 minus to give N2 plus 4 water molecules plus 3 S4O6 2 minus. Okay, so let's do the final check through again. 8 hydrogens, 8 hydrogens. 2 nitrogens, 2 nitrogens. 4 plus 18 oxygen, so that's 20. 4 plus 18 oxygen, so that's 20 oxygens. We have 12 sulfurs, and then the charges, we have plus 8, minus 2, minus 12. So that gives you what? 8 minus 14, which gives you minus 6. We have 3 times minus 2, minus 6. So now we're confident that this equation is the final answer. All right? Okay. All right. Any other questions about this? Any other questions? Okay, so what's next to talk about? in this chapter. Nothing much, really. What you see here on the screen is the oxidation number of certain nonmetals in groups 5A, 6A, and 7A. And what you'll find is that when these elements combine with other atoms or even by themselves, the range of possible oxidation numbers is dependent on the group number. So for example, in group 5, and you're using nitrogen as an example, you can have the oxidation number going from a high of +5 to a low of -3, right? And if you look at the correlation between the high and low, you'll see that the 5, if you look at the, what do you call it now? If you look at 5 + 3, that gives you 8, which would represent, of course, the octet situation in atoms in the what do you call it now? The representative group. So that's the situation for group 5A. In the case of group 6A, can go from +6 high oxidation number to -2 as a low. In the case of group 7A, it can go from +7 to -1. All right, so those are the possibilities for those specific groups, right? So as stated here, the maximum number in terms of the oxidation number would be equal to the group number. The minimum number would be equal to the group number -8. All right. And it says here that species in the middle of their oxidation number range can act as either oxidizing or reducing agent. The ones that have the high oxidizing or oxidation number can behave as oxidizing agents in reactions, and the ones that have the low oxidation numbers in terms of the extreme down here, for example, in the case of ammonia, will tend to behave as a reducing agent. And you can see a similar correlation for what happens in group 6A and group 7A, all right? Now, the only other thing that's left in this chapter to talk about is this discussion about metals. And metals typically behave as reducing agents. In other words, they tend to give up electrons in their reactions. Of course, they do so to different extents, and you can actually order them according to their strength as reducing agents. And that order is called the activity series. And this is basically what the activity series looks like. So as you can see here, the most powerful reducing agent in this list is potassium. And then the least powerful in this list is silver. All right. And basically we can use this series as a way of predicting certain displacement reactions, in that the metal will displace from solution the ions of any metal that lies below it in the series. All right. So we can make certain predictions about certain reaction taking place. For example, we can predict that zinc will replace hydrogen in hydrogen chloride to form the products as you can see here. Why? Because zinc, if you look at zinc and if you look at where hydrogen is, zinc is above hydrogen. So therefore, we are fairly confident that zinc will displace hydrogen from hydrogen chloride or hydrochloric acid, right? And we can also say that the reverse reaction will not take place. In other words, hydrogen will not replace zinc from zinc chloride to form zinc and hydrochloric acid. So we can use this as a guide to help us to predict the direction of certain single displacement reactions. Okay, now the rest of this chapter involves looking at different analytical techniques. I won't go into it. Instead, I will direct you to your textbook where it is located so that you can read this up on your own. And in your textbook, if you go to page section 4.5, which is page 201, let me bring it up. Where is it? Let me bring it up. Let me see if I can find it. I think this is it. All right. So if you go to page 201, I just want to show you what it looks like, where it talks about the different ways of analysis, and in particular, different types of chemical analysis. And in particular, it discusses titration, all right? That's the one that I really want to point out here. So I want you to read this. It also goes into other analytical techniques. Let me scroll down here. It gives an example. You need to look at that as well. And then they talk about gravimetric analysis. So you can look at that as well. And it gives an example as well of a gravimetric analysis problem. And then it talks about combustion analysis, which we covered already. So you can go ahead and look up that and do the problem example that they gave as well. In addition to reading that section, right, section 4.5, pages 201 to 207. Let me make sure I'm telling you the right pages. Yes, 201 to 207. There's a YouTube video. Let me see if I can bring it up here, which shows you how to do titration in practice. So if we were doing labs on campus, you're definitely going to, you would have definitely be doing this particular type of analysis. So what I'm going to do is copy the URL for this, and I'm going to paste it. Okay, how am I going to do this? I'm going to paste it in the chat. Where's the chat? Oh, chat is here. All right. So that's the video that I expect you to watch. And it goes into basically the practical aspects of titration analysis. All right. You know, the type of glassware that you use and how you go about manipulating the glassware in order to carry out the analysis. All right. So make sure that you read the section in the textbook that I pointed out. Again, that's page, section 4.5, pages 201 to 207. And make sure you watch this video as well. All right. So that basically represents the end of this chapter. All right. Let me just, right. That basically represents the end of this chapter. So the next chapter is chapter 5, which deals with gases. So that's what we're going to get into right now. Okay, so I'm quite sure we're all familiar with the 3 states of matter: solids, liquid, and gases, right? And even without any detailed expert knowledge of the nature of gases and solids and liquids, one can tell basically that gases behave far differently from solids and liquids in many respects. For example, you can easily compress a gas by reducing its volume, more so than when it comes to solids and liquids, right? So you can literally, for example, have the volume of a gas, for example, relatively easily. But in the case of solids and liquids, that's very difficult, all right? So what you'll find is that the laws governing the behavior of gases is different from the laws that govern the behavior of solids and liquids. So that's what we'll be looking at in this chapter. So, of course, the question we'll be dealing with here is, what are gases like? And if you look at gases at the microscopic level, and this is something you should have been exposed to, again, from your high school or introductory chemistry courses, you'll see that gases are composed of very small particles, molecules, atoms, and they're always in constant random motion, all right? And as a result of that particular microscopic property, then that imparts certain macroscopic properties of gases in that they flow readily and they occupy the entire volume of their container. And this is something, of course, we're all familiar with in terms of how gases behave. Now, at this juncture, I want to talk about the term that you'll see here that is oftentimes referred to, vapor, all right? And this is a term that is used for a substance which is normally a liquid at room temperature and pressure, but when heated will be converted to a gas. So the gas in this particular context is normally called a vapor. So therefore, we would use the term vapor in association, for example, of water or methanol in the gaseous state, because normally water and methanol would exist as a liquid under normal room temperature and pressure conditions. On the other hand, in the case of gases such as oxygen and hydrogen, which exist as a gas under normal room temperature conditions and room pressure conditions, we simply use the term gas. We don't use vapors when it comes to those substances, all right? Okay, and what you'll find is that many low molar mass molecular compounds will be easily converted to vapor by heating, all right? Or they exist as gases, all right? So for example, oxygen and hydrogen, their molar masses are relatively low. And in terms of liquids, water and methanol, again, you know, their molar masses are low, but they can be easily converted to vapor, all right? When it comes to higher molar mass liquids, they tend not to be so easily converted to vapor. Okay, so what you see here in this slide is basically a list of different gases and their uses, all right? So as you can see, these are substances that impact our lives every day, and we don't even think about it. For example, acetylene is a gas that is used as a fuel for welding metals. Just to pick another arbitrary example, chlorine is a disinfectant and serves as a bleach. Methane is used as a fuel and also used in the manufacture of hydrogen. And propane is basically a fuel used for cooking gas, for example. All right, so these are just some examples of different gases. All right, okay. Now, the model that is used to explain the behavior of gases is called the kinetic molecular theory, all right? So basically, if you understand this, then you can understand why gases behave the way they do, and you can understand also why gases obey certain laws, right? So basically what this theory is saying is that the particles, the molecules, are energetic and they're always moving in rapid motion, all right? And they tend to display what we call translational motion, which is basically straight line motion, unless they collide with each other or collide with the walls of the container. All right. Now, if you understand that picture, right? If you have that picture in your head about how the gas molecules behave, then you can understand why, for example, gases exert pressure on the walls of the container that they're in. And the reason why that is because that pressure is a manifestation of the constant and continuous bombardment of high-speed molecules against the wall of the container, right? So the fact that the gas can exert pressure on the walls of the container is due to the fact that billions of molecules are always hitting the walls of the container because they're always moving at fast speeds. And when I say fast speeds, I'm talking about speeds around the order of 1,000 meters per second, of course, depending on the temperature, which is another factor that we can also understand with respect to the kinetic molecular theory. Because as we're going to see later on, the higher the temperature of the gas, the greater will be the speeds of the gas particles. And therefore the average speed will be greater, and they will hit the walls of the container with greater frequency and greater speed. And therefore, again, the pressure would increase. And that's a reason why as you increase the temperature of a gas, the pressure would increase, all right? So those are just two properties of gases that we can observe at the macroscopic level that are explained very well by the kinetic molecular theory. And we're going to get into a more quantitative relationship between pressure, temperature, the average speed of the gas molecules, and all of that later on, all right? Okay, so that's basically an introduction to the kinetic molecular theory. We're going to see some more quantitative aspects of the kinetic molecular theory later on, but this is just a brief introduction to this particular theory. Okay, so we talked about gas pressure. Excuse me 1 minute. We talked about gas pressure, all right? So let's talk about what we mean by this term pressure, because in everyday language, normal people, non-scientists, tend to confuse the terms pressure and force as if they mean the same thing, all right? Now in science, these are two different things, even though they're related, because force is basically a push or a pull, right? That's basically what force is. Pressure is the force transmitted over a particular area, all right? As you can see here on the screen, it is a force per unit area, all right? So therefore, according to the SI system, the force is expressed in newtons and the area is expressed in square meters. So therefore, since pressure is equal to force per unit area, then the units of pressure based on that definition would be newtons per meter squared. And there's a name given to this pressure. It's called the Pascal unit, all right? So the Pascal unit is the same thing as newtons per meter squared, all right? Now, it turns out that this is not the only unit of pressure. You can actually, of course, apply the prefixes that we use in the metric system to the Pascal unit to get larger or lower or smaller values of, or smaller units of pressure. So very often we use the kilopascals. It turns out that this is more convenient than the pascals in terms of the pressure of gases. So you can see this in some cases. And of course, you should be able to convert from kilopascals to pascals. because kilo means 1,000. So therefore 1,000 pascals is equal to 1 kilopascal, all right? And there are some other units as well that is used in science. One is the atmosphere, all right? We're gonna talk about how we come about with this unit here. And then we have what's known as a millimeter mercury unit. We're gonna explain what that means. And it turns out that there's yet another unit, the torr unit, and the torr unit and the millimeter mercury unit are the same, right? So 1 millimeter mercury is equal to 1 torr. In fact, there is a relationship between all these units, which is shown on this slide right here, right? So the way this is set up, you have 1 atmosphere here, and its stated equivalency in different units are shown here on the right side. So as you can see here, 1 atmosphere is equal to 760 millimeters mercury, which is also equal to 760 torr. Remember I said that the millimeter mercury unit and the torr units are both the same. We have the 1 atmosphere equal to this amount of bars, this amount of millibars, this amount of pounds per square inch. And then we have the newtons per meter squared, which I mentioned before, right? So 1 atmosphere is equal to 101,325 newtons per meter squared, which is the same thing as 101,325 pascals. And of course, to get from pascals to kilopascals, we divide this by 1,000 to get 101.325 kilopascals, all right? Now, for our purposes in this course, we will be using the millimeter mercury unit, the torr unit, the newtons per meter squared unit, the pascals and the kilopascals. To be perfectly honest, I do not foresee us using the bar unit or the millibar unit or pounds per square inch. There may be 1 or 2 examples where we may use these 3, but we hardly use them in the metric system, all right? Okay, so basically that's the relationship between the different pressure units, all right? Okay, so how do we measure pressure? Well, it depends on what you're trying to measure the pressure of, all right? Now, if you want to measure the pressure of the atmosphere, then we use an instrument that is called a barometer, all right? Now, as you know, the atmosphere, the air we breathe, is a mixture of different gases. The major component would be nitrogen, which is about 78% of the total gaseous mixture. Then you have oxygen, and then you have some other gases present, all right? So of course that mixture of gases will exert a pressure on everything that is submerged within it. So as we're walking around the earth and doing our activities, we are actually experiencing the pressure exerted on the atmosphere, by the atmosphere on our bodies, all right? So basically, how do we use a barometer to measure the atmospheric pressure? So we need to remind ourselves of the relationship between some of the units that we discussed. 1 atmosphere is equal to 760 millimeters mercury, which is equal to 760 torr, which is equal to 100.325 kilopascals. So you have to take this into account. And in fact, what we're going to see here is how the mercury barometer is what is responsible for coming up with this unit, the millimeter mercury unit. In fact, here's a definition of the relationship between the atmosphere unit and the millimeter mercury unit. 1 atmosphere, by definition, is the pressure exerted by a column of mercury exactly 760 millimeters high, all right? And we're going to see it in this diagram here. So what we're looking at in this diagram here are 2 troughs filled with mercury, and the choice of liquid in this case is very important, which we're going to explain later on, all right? And in each trough of mercury, we have 2 tubes, right? Now you'll notice that the difference between these 2 tubes is that this tube is open at both ends, right? So one end is submerged below the surface of the mercury and the other end is open to the atmosphere, right? Now what you'll find, and I'm quite sure you would know this from your everyday experience, what you'd find in this case is that the mercury level inside the tube here will be exactly at the same level as the mercury level outside in the trough, right? And the reason why that is so is because the atmospheric pressure acting on the surface outside will be equal to the atmospheric pressure that is exerted through the tube here, through the opening of this tube on the surface inside that tube, right? So therefore they balance each other out, and therefore as a result, the mercury level here is the same as the mercury level outside, all right? No surprise there. Now in the case of the other setup right here, let me just explain how this is set up. So basically what you have here is your mercury in the trough. And then what you would do before you submerge this tube inside the mercury here, you would completely fill this tube with mercury, right? Make sure it's all full. And then you invert it such that the mouth is submerged under the surface of the mercury in the trough, right? And then you leave it to stand for a while. And then what happens is that if this tube is long enough, you'll find that the mercury level is going to fall until you see that the height difference between the mercury level here inside the tube and the mercury level here outside the tube is about 760 millimeters mercury. So what that means is that whatever the pressure that is exerted on the surface here, right, outside the tube, would be equal to the pressure at the same level here exerted by this column of mercury right here, all right? And you'll notice that there is a space right here, which is effectively a vacuum, right? Not technically true, but basically you're going to have mercury vapor here, but the vapor here, the pressure exerted by the vapor here is so low, it's almost zero, that it's in effect a vacuum, right? So basically this is where the millimeter mercury unit comes from. Basically what this is saying is that 1 atmosphere, which is the pressure of the atmosphere that is exerted on the surface of the mercury here, will be equal to the pressure exerted by a column of mercury, which is 760 millimeters high. So that's where we get that particular unit from, okay? Okay, so that's where we get 1 atmosphere is equal to 760 millimeter mercury. Okay, so that's how the mercury barometer works, all right? Okay, before I move on, are there any questions about the mercury barometer? Any questions? Okay, so here's a simple example, nothing too complicated about this. Question is asking, what is the pressure of this value expressed in kilopascals? What is the pressure in torr? That is a very simple problem. It's basically a unit conversion problem. You start off with the 100.2 kilopascals, and you multiply by the conversion factor, which relates the torr unit to the kilopascal unit. And if you remember, we said that 760 torr is equal to 101.325 kilopascals. All right, and we work that out. Let me do that on my calculator. 0.2 times 760 equals divided by 101.325. And the answer I got rounded off to 4 sig figs will be 751.6 torrs, all right? Okay, so that's basically how we do that problem. So that's a relatively simple problem. I don't think there's anything too complicated about that. So let's move on to the next instrument that we use with respect to measuring pressures. And we use this instrument called a manometer to measure the pressure of a gas. So in other words, if you have a gas trapped in a container and you want to measure the pressure of that gas, then this is the instrument that you would use to do so. Again, so that's what the manometer is. Again, we use the difference in the heights of mercury. It says or other liquid, but mercury is actually the liquid of choice that is used when it comes to the manometer in the 2 arms of this particular instrument. Okay, so just to show you what we're talking about here, this is an example of a manometer where you have a U-shaped tube, so to speak. One end is connected to the container which has a gas. You have mercury inside here, and in this particular case, we have no air here. We basically have a vacuum here, so the pressure exerted here will be 0, right? So when you open up the stopcock here, and the gas flows through, it's going to exert pressure on this end, right, this surface here, and pushes up the mercury level in the other tube. And the height difference between the 2 mercury levels on either side of the U-shaped tube would be equal to the pressure, right? So we can simply, for example, write down that the pressure of the gas is equal to whatever the height difference here is in terms of millimeters mercury, all right? So as stated here, P gas is equal to delta H, all right? So that's how we can determine the pressure expressed directly in millimeters mercury. Now, you can also determine the pressure expressed in pascals, but you'd have to use not only the height difference here, but you have to use this equation which contains that height difference. So this H here would represent the delta H right here, right? However, you also have to use this constant here, which is known as the acceleration due to gravity. This is a constant if you do physics, or if you plan to do physics, you're going to meet this in your physics courses. It basically represents the acceleration of an object as it falls to the earth, all right? That's basically what it means, right? And D would be the density of the liquid, which in this case, again, would be mercury. Now, please note that in using this equation, you have to be very specific and careful about the units that you're going to use it, that you'll be using, right? So as you can see here, the units of the acceleration due to gravity is meters per second squared. The units of density must be expressed in kilograms per meters cubed, and the H here must be expressed in meters. So you'd have to convert this, which would probably be recorded in millimeters mercury, to meters of mercury, all right? So once you get the units right and you plug the numbers into this equation, then your units of pressure would be pascals, all right? So that's basically how you would use this equation to calculate the pressure in pascals based on this setup right here. So that's what we call a closed end manometer, right? Because this end is closed. But there's also another type of manometer, which is known as the open end manometer, right? And here we have in this particular slide, two situations where you have an open end manometer. So in the case of an open end manometer, you have the U-shaped tube, but this end is open. The other end, as before, is connected to the container, which has a gas. And in this particular case, for this setup on the left, when the gas is allowed to flow through, it exerts pressure right here, right? So you have pressure exerted on the surface on this side of the manometer, but you also have the barometric pressure or the atmospheric pressure exerted on this side of the manometer, right? So P bar is basically representing the barometric pressure, which is the same thing as the atmospheric pressure. So if you hear me use the term barometric pressure, it's the same thing as the atmospheric pressure, right? Okay, so obviously, because this end here, the mercury here, is pushed to a lower level compared to here, that tells us that the pressure exerted by the gas is greater than the barometric pressure. And the difference between this pressure and this pressure would be represented by the height difference between the two mercury levels. So therefore, that's a reason why the relationship between P gas, delta H, and P bar is given by this equation. P gas will be equal to P bar plus delta H. P gas will be equal to P bar plus delta H, and that's the equation right here, right? And therefore, you can rearrange this to solve for delta H if you know what the pressure of the gas is and if you know what the barometric pressure is, all right? Okay, so that's one situation on the left. On the right, you have a situation where basically things are flipped in that the pressure exerted here would be less than the pressure exerted here. Again, the difference between these two pressures would be equal to the height difference between the two mercury levels on either side of the U-shaped tube. So therefore, we can write down a mathematical relationship between P bar, delta H, and P gas in this situation. And that relationship would be P bar is equal to P gas plus delta H, right? So that's why we have this relationship here. P bar is equal to P gas plus delta H. And again, if you know what P bar is and if you know what the pressure of the gas is, then you can calculate what delta H is, all right, the difference between those two, all right? In fact, if you know two of these, you can determine the third value, all right? So basically, you have to be careful when using an open-end manometer to determine which equation you're going to use to determine the pressure of a gas. In fact, it says here, as an example, for part B, what is P gas if delta H is 100 millimeters of mercury and P bar is 760 millimeters of mercury? Well, basically all you have to do is find the difference between P bar and delta H, right? So the answer here, write this down, where should I write this? Let me try to squeeze it. Okay, let me try to squeeze it here. So basically you're asked to find P gas. So P gas would be equal to P bar minus delta H. And that means that P bar is 760 millimeters of mercury minus minus delta H, which is 100 millimeters of mercury. So the final answer becomes 660 millimeters of mercury. And that's how you do that. All right. So that's basically how you would calculate delta H. I'm sorry, not delta H, the pressure of the gas in this case. All right. Okay. Any questions about the open end manometer or even the closed end manometer? Any questions? Okay, so continuing. Okay, now this example here shows you what I was talking about. It's an example that shows you why mercury is a liquid of choice for, you know, the instruments that we talked about, the manometer and the barometer. So this question says, calculate the height of a column of mercury, a column of water, and it gives you the density of water that exerts the same pressure as a column of mercury, and it gives you the density of mercury, 760 millimeters high, all right? So the first thing I would do is I'd write down the equation for calculating the pressure of a mercury column, right? If you remember, this is the equation. Pressure is equal to H times G times D. H is the height of the column of the liquid, G is the acceleration due to gravity, and D is the density. The next thing I'm going to write down is an equation which basically states that the pressure of the water is equal to the pressure of the mercury column. And the reason why we say that is because that's what the question says. It says that the water column exerts the same pressure as the mercury column. So that's why I wrote this down. So what I'm going to do now is replace this and this with their respective forms of this equation. So for PW, I'm going to write down HW times G times DW. HW would be the height of the water column, G would be the acceleration due to gravity, and DW would be the density of the water, right? And then on the right side of the equation, I'll replace this with the height of the mercury column, HG, times, again, the acceleration due to gravity, times the density of the mercury column, all right? And then the next thing I would recognize is that since we have G on the both sides being the same, they can cancel out. And what we're trying to calculate is the height of the water column. So to isolate this on this side, I would divide both sides by the density of water, right? So when I divide this by the density of water, this cancels out with this. So I end up with the mercury height times the density of mercury divided by the density of water, which is what I have down here. Part of it is cut off, unfortunately. So let me write that up here. So basically, you're going to have HW is equal to H mercury times the density of mercury divided by the density of water, right? And then I plug the numbers in. So you're going to have 760 millimeters, 60 millimeters here times the density of mercury, which is 13.6 grams per cm cube, divided by the density of water, which is 1.00 grams per cm cube, all right? And if you do the calculation, you're going to
find— On the left side?
I'm sorry?
Is that DHY?
No, DHG, I'm sorry. Mercury. That's a symbol for mercury. HG. Got that?
Yes, sir.
Okay, good. All right, so as I was saying, when you plug these numbers in, you're going to get the answer being equal to 10,300 millimeters, all right? And this is equal to 10.3 meters, right? So basically, if you were to use water, which is very cheap, right? Water is like the cheapest liquid around, right? If you were to use water instead of mercury to construct, for example, a barometer, you would need a tube which would be 10.3 meters high, right? Now, I don't know if you know what 10.3 meters look like. But just to give you an idea, and I don't know how many of you know me in person, my height is about 6'5", right? Which is just under 2 meters, right? In fact, I think it's about 1.98 meters, right? So basically, if you were to use water instead of mercury for a barometer, you're going to need a column or a tube, which is 5 times my height. And as you can imagine, that it would be a very inconvenient piece of glassware to be used for this purpose. And this underscores the reason why mercury is the liquid of choice, right? If you use mercury, then you only need a tube, which is 760 millimeters high, which is less than a meter, all right? And the main reason why that is so is because of the high density of mercury. Mercury has a density of 13.6 grams per cm cube, while water has a density of 1.00 grams per cm cube, all right? So this example explains why mercury is a liquid of choice, even though it's a very expensive liquid, and it's also very toxic. But basically, those two cons or downsides pale in comparison to the price, or I should say to the convenience of using a shorter color. And that's the reason why mercury is a liquid of choice for this type of instrumentation. Okay, any questions about this example? Any questions? Okay, what time is it? Let me see here. Okay, we have enough time. Okay, so what we're going to look at are a series of different laws, all right, that govern the behavior of gases, right? And these are all laws that can be expressed quantitatively, in most cases as equations, and they're all explainable by the kinetic molecular theory, all right? So the first law we're going to look at is Boyle's law, which is a law which describes the relationship between the pressure and the volume of a gas. And the law can be stated in different ways. If you express it in words, you can say, for example, for a fixed amount of gas at a constant temperature, the volume of a gas varies inversely with its pressure. So this is one way of expressing it in words. Another way of expressing it is that for a fixed amount of gas at a constant temperature, the product of the pressure and volume is a constant, all right? And there is an experiment that I would normally do, pre the pandemic, which is a very elegant experiment. I wish you guys could actually do it, because you'll see that, by doing this experiment, you see Boyle's law being proven very elegantly and quantitatively. Unfortunately, we can't do it. I think for my lab classes, I may give you a handout with the data to do this as a lab exercise. But I mean, this experiment that we would normally do is a very beautiful experiment. I really wish you guys would be able to do it. In any case, so that's how we express the law in words. And then we can express it in terms of an equation where it can be expressed this way: PV is equal to a constant, or P initial times V initial is equal to P final times V final. Me personally, I prefer to express it this way: P1 V1 is equal to P2 V2, all right? Which is basically the same thing as expressing it this way, all right? Now, key thing you need to remember about this equation, and that is that this equation will only work if the temperature is constant and if the amount of gas is constant or fixed, all right? So if the amount of gas is fixed and the temperature is constant, then this relationship will hold. If you vary any one of those two, then this equation will not hold, all right? So that's an important thing that you need to recognize about this equation. Okay, so the next slide here shows you a graphical representation of Boyle's law. In this case here, we're plotting pressure versus volume, right? And you'll notice that there's a smooth curve. And if you continue the curve this way or this way, in either case, the curve will approach each axis, but will not touch it, all right? And that's because if you rearrange, write it here, PV is equal to a constant, then we can rewrite this as P is equal to K times 1 over V, where P would be representative of what is on the y-axis, and 1 over v, or v, would represent the x values, all right? And if you know anything from your math course, y equal to a constant times 1 over x would give this shape, all right? So that's basically what happens when you plot p versus v, all right? And you'll notice also, if you look at the numbers, you see the inverse relationship. For example, let me start from, how should I do this? Let me start from, okay, let me start from here. So at this value V, whatever it is, right, the pressure is 4.0 atmospheres. If you suddenly reduce the volume, or increase the volume, I should say, from V to 2V, in other words, you double it, then the corresponding pressure is halved from 4.0 to 2.0. And if you continue to increase the volume, again, by doubling to 4V, you see that the pressure, again, is reduced by half from 2.0 to 1.0, all right? So that shows you, again, the inverse relationship between pressure and volume. Now, the graph over here shows you a linear relationship, because what they're doing here is plotting 1 over P versus the volume, right? So if I were to reduce, or I should say rearrange this equation here, I would put, how would I arrange this? I would say that I would switch these two. So V would be equal to K times 1 over P. And let me see here. And then 1 over P would be equal to V over K, which would be equal to K prime, which is another constant, times V, right? So in this case here, this would be plotted on the y-axis. The V would be plotted on the x-axis, right? So it's the 1 over P that is plotted on the y-axis, and the V will be plotted on the x-axis, all right? And if you look at this carefully, you'll see that this is basically the equation of a straight line, right? Y is equal to mx, right? So therefore, when you do that plot of 1 over P versus V, you get this straight line here, all right? And of course, you can do things with the straight line. For example, you can find out where it intercepts on the y-axis. In this case, it should intercept at 0. And you can find out what the slope is, which is equal to m, all right? Okay, so those are just two ways of graphically representing Boyle's law. Okay, any questions about this particular slide? Okay, so let's look at a question based on what we have just covered. So the question talks about a helium-filled party balloon, which has a volume of 4.50 liters. The pressure, atmospheric pressure, is 748 torr at sea level, where the balloon is initially. And then it says that the temperature remains constant. So that should give you a hint that we're talking about Boyle's law. The fact that they gave you the volume, they gave you the pressure, and they gave you the fact that the temperature is constant, which is one of the requirements for Boyle's law to work. So the question is asking, what will be the volume of the balloon when it is taken to a mountain resort at an altitude of 2,500 meters, where the atmospheric pressure is lower, 555.7 torr, all right? Okay, now before we do this question, I have a very interesting question to ask you. Why is it you think, and I just want to hear what you think the reason is for this. Why is it that in elevated areas, you think that the atmospheric pressure is lower compared to sea level? As stated here, at sea level, the atmospheric pressure is 748 torr, but in elevated regions like mountains and so on, the atmospheric pressure is 557 torr. Can anybody come up with a reasonable answer to that question? Why is it that at elevated areas, the atmospheric pressure is lower compared to sea level? Anybody? Well, anybody want to take a stab at this? Come on, no idea? Okay, since you guys have given up on this one, the reason is that the Earth pulls the atmosphere to its surface, right? So the bulk or the the bulk of the mass of the atmosphere would be closer to the surface compared to elevated areas. And therefore, as a result, the density of the atmosphere is higher, which means that the pressure exerted by the atmosphere at sea level would be greater compared to the pressure exerted by the atmosphere in elevated areas where the air is thinner and less dense. All right, so that's the reason why you have that pressure differential between elevated areas and sea level. Okay, so the equation we're going to use for this question is P1 V1 is equal to P2 V2. All right, so when you're doing a question like this, you need to identify the terms in the question itself. So the question says that the initial volume is 450 and the initial pressure is 748 torr, and it tells you that the final pressure is 557 torr. So therefore, the initial volume here is the 450. The initial pressure here is the 748, and the final pressure here, P2, is the 557 torr, right? What the question is asking for is V2. So we can algebraically rearrange this equation to get V2 is equal to P1 V1 over P2. And then all we have to do is plug the numbers in. So P1 is 748 torr times V1, which is 4.50 liters, divided by P2, which is 557 torr. All right, and then you do your number crunching. This will cancel out with that. So let me do this on my calculator. 748 times 450, I'm sorry, 4.50 divided by 557. And according to my calculations, this works out to be equal to 6.04 liters, all right? So that's basically how you'd solve this problem, okay? Now, one thing I want to say here at this juncture is that when you're using Boyle's law, you have to be careful about the units, right? And in fact, what you have to take care of is making sure that the units for the corresponding terms on either side are the same. In other words, the units for P1 and P2 must be the same, right? It could be atmospheres, it could be millimeters mercury, it doesn't matter, but they must be the same on both sides, right? And the same is true for the volume units, V1 and V2. They must be the same. So V1 and V2 could be expressed in liters or they could be expressed in centimeters cubed. It doesn't matter. As long as they're the same on both sides, then you can plug them into the equation directly and use them, all right? So you may encounter a problem in the future where, for example, P1 is given in torr and P2 is given in, let's say, kilopascals. Then you need to either convert the torr units to kilopascals or vice versa before you plug them into this equation, all right? And the same is true for V1 and V2, all right? Okay, any questions about this example? Any questions? Any questions? Okay, so another law we're going to look at is Charles' law, and this law relates the volume of a gas to the temperature of a gas. And we know from everyday experience that as you increase the temperature of a gas, the volume would increase. And in words, Charles' law says that the volume of a fixed amount of gas at a constant pressure is directly proportional to its Kelvin temperature, or the Kelvin temperature is also called the absolute temperature, all right? And if you recall, we talked about the fact that there's a relationship between the Kelvin unit and the Celsius unit given by this equation here, right? And we're going to see that this equation comes directly from a discussion of Charles' law, all right? So let's talk about absolute zero before we get to Charles' law directly. Absolute zero is the temperature that basically is obtained as a result of extrapolating the graph that you're going to see shortly to zero, right? And what this represents is a theoretical concept where if the gas existed at that low temperature, then the gas particles will have absolutely no kinetic energy. In other words, it would just collapse into a singularity of zero volume. It has no kinetic energy, no translational, no rotational, no vibrational energy, all right? So that's a theoretical concept. And to the best of my knowledge, and I need to look this up, but to the best of my knowledge, absolute zero has never been achieved in this context, all right? But it's a theoretical concept that is predicted based on what Charles' law suggests, all right? So as a result, absolute zero on the Kelvin scale is equal to minus 273.15 degrees Celsius. And what that means is 0 Kelvin is minus 273.15 degrees Celsius. Okay, so let us get to this graph here, which shows you how that relationship came about. So what we have here is for a gas, we plot the volume versus the temperature in Celsius, right? So this person who did this experiment collected data and plotted it, and basically this person got a straight line, right? Now we all know that below a certain temperature, if you cool the liquid, or I should say cool the gas to a low enough temperature, it will start to liquefy, right? So therefore there'll be no gas that exists below a certain temperature, all right? So what this person did was extrapolate this line until it cuts the x-axis. And it turns out that it cuts the x-axis here at minus 273, minus 273.15 degrees Celsius, right? And as I said before, that represents where the volume is equal to zero. If it cuts the x-axis, that means that the volume reading would be zero here, right? Which, as I said before, represents a point. If the gas were to exist at that low temperature, the gas molecules will have no kinetic energy whatsoever, all right? So what was decided by the powers that be back then was that they would develop a new temperature scale called the Kelvin scale, where this is called 0 Kelvin, right? But the actual magnitude of the units would be the same as the Celsius unit, right? So if this is 0 Kelvin, that means that 0 degrees Celsius here would be 273.15 Kelvin. And that's where we get the relationship, as I said before, which is the temperature in Kelvin is equal to the temperature in Celsius plus 273.15. 273.15. So that's how we convert the Kelvin, or I should say the Celsius value to the Kelvin value, all right? So that's basically what is represented here. It's tantamount actually to moving this y-axis over to where it cuts here, and we end up with this graph right here, right? So basically, that's how we end up with the Kelvin scale as a result of Charles' law, all right? Now, let me go back to Charles' law here, because I just remembered I should mention something here about the Charles' law, which is very important. Charles' law will only work if the amount of gas is fixed and if the pressure is constant. So constant pressure, right? So those two things are necessary for Charles' law to work. And we can represent Charles' law mathematically as V1 over T1 is equal to V2 over T2, all right? Now, let me check something here before I move on. Okay, now going back to this should be T2 here. Now, it doesn't matter what V1 and V2 units are, as long as they're the same, right? So V1 and V2 units must be the same. All right? But T1 and T2 must be expressed in Kelvin. All right? Very important. All right. So if you're given a question where you're given the temperature in Celsius, if you're to use Charles' law, you must convert those temperature values to Kelvin. And we do that by adding 273 to the Celsius value to give the temperature value in Kelvin. And then you plug it into the equation. The V1 and V2 units can be anything. They can be liters, they can be centimeters cubed, they can be gallons, it doesn't matter, as long as they're the same on both sides, all right? Okay, so based on what we have just covered here, should be able to do this example. So the question says you have a balloon indoors where the temperature is 27 degrees Celsius and it has a volume of 2.0 liters, 2.00 liters. And then you take the balloon outside where the temperature is minus 23 degrees Celsius. And it says assume no change in gas pressure. So this should clue you in to the fact that this is a Charles' law problem. So therefore, we write down Charles' law, V1 over T1 is equal to V2 over T2. What the question is asking for is the volume outdoors, which would be V2. So to get V2, we multiply both sides by T2. So basically V2 would be equal to V1 T2 over T1, all right? Now, we have to identify the different terms. T1 is 27 degrees Celsius, but we have to convert that to Kelvin. So 27 plus 273 gives 300 Kelvin. So this would be T1 equals 300 Kelvin. And then they gave you V2. So this is V2. I'm sorry, V1. They gave you V1. And they gave you T2. Now T2, again, you have to express it in Kelvin. So that's minus 23 plus 273. So that's 250 Kelvin. 250 Kelvin. So we plug these numbers into this equation. So V1 is 2.00 liters times T2, which is 250 Kelvin, all divided by T1, which is 300 Kelvin. And then we put the numbers in, 2 times 250 divided by 300. And according to my calculations, when rounded off to 3 fifths, this is going to be equal to 1.67 liters, because the Kelvin units will cancel out here and here, all right? So that's basically how this Charles' law problem will be solved. Okay, any questions about this? Any questions? Any questions? Oh, 10:40. Okay, we have 5 minutes left. Let's see what we have on the next slide. Okay, I think I'm going to stop here because I don't want to start this topic and then stop in the middle of it. Let me just check something here. Yes, I think I'm going to stop here. All right. So that's basically it for today. If there are no, are there any other questions, any general questions, any problems you want to discuss in the 5 minutes that we have left? No? Okay, so that's it for today. So I guess I'll see you guys on Thursday. So enjoy the rest of your day and I'll see you then. All right, so take care.